Okay. Thank you.
It will be really
Rob
did it before.
I think
Are you traveling or are you just back?
Okay, that looks good.
Okay, hi everyone. It's a great pleasure, to welcome you here into the probably last, maybe second to last, one in the series. Today's topic is really the intra-halo medium, and we have two very great speakers here. We start today first with Rob Simcoe. Many of us know, of course, Rob. He's working down at MIT. He's there a full professor for physics. He's also the director for the Kali Institute down there, and he did his PhD down in Caltech in 2003, and then basically moved to the MIT as a Pollard fellow, and then joined there the faculty in 2006. As you also know, he does a lot of instrumentation. One of his strong interests is really to develop optical as well as infrared instrumentation for ground-based astronomy. And he's the PI as well as the science PI for the FIRE instrument. Of course, he's a world-leading expert in observations of high redshift galaxies as well as in the intergalactic medium out there. And so I think we're very fortunate today to have this excellent speaker to talk to us about the observational perspective on the intra-halo medium. So Rob, take it away.
Thank you. Thanks. And we'll introduce Cameron after. Okay.
Yes.
Thanks for having me. This should be fun. I was told to sort of review things, but I'll sprinkle in a little bit of stuff that's new, but not too much. So I had suggested changing the title of this from the Circumgalactic medium to the intra-halo medium in an effort. I was supposed to be somewhat edgy. It's not too much so, but I just want to explain briefly, just to remind everybody, that we are used to, you hear about people discussing the circumgalactic medium, and if you want to put some scales on this, so the stellar content of the M81, M82 group is shown there, where M82 is the thing that's always shown as the example of winds that are going to pollute the IGN from star formation that's going on in the central area. You see how big it is relative to M81. So people talk about the circumgalactic medium as being the area that's sort of outside of these galaxies. But the galaxies themselves live in a larger environment. So this is what the gas content, this is an H1 image from the Green Bank telescope of the same system on the same scale. And so the separation between these two on the sky is about 40 kiloparsecs. And it's the baryonic mass of this group is about of order 10 to the 10 solar masses. And so this is a modestly deep image that tells us something about what's going on outside of the disk. But this stuff is very much still inside the galaxy, right? This is not, it's circumdisk, but it's not circumgalactic. Because if you zoom out even more, the dark matter halo for this group would be about this size. So R200 for the M81, M82 group is about 210 kiloparsecs. And so this tells you where it is. Most of the observations, so I was supposed to focus on observations today, and so most of what I've done and others, and a lot of the information we have about this intra-halo medium, which I'm going to call it intra-halo because it's sort of in this area here, but it's well inside the virial radius. It's part of the galaxy, okay? So, and so you can use those terms somewhat interchangeably, but let's just not forget that. This whole area is filled with a gas that's at the virial temperature, which is about 1 million degrees. So you're in equilibrium inside this halo if you're at 1 million degrees. And the dark matter mass is about 10 to the 12 solar masses, so about 30 times higher than the baryonic mass. So this stuff that's in the middle here is really just a condensate that's in the middle of this halo. Okay? And what we call circumgalactic is just stuff that's still in the galaxy, but at a little bit larger distance. Okay? And the question that Cameron will answer today is how stuff gets in and out from here, right? So I want to divide this into a few areas where first I want to talk about things that we think we know about the intra-halo medium, and we really do, that they're fairly model independent. And then I'll talk about things that we are said to know, right, or we think we know, but are really model dependent. And I'll talk about where those dependencies come in. And then a little bit more speculative stuff at the end. So things that are very model independent. We know that if you are within roughly 50 kiloparsecs of the center of a halo like this, and you look at a quasar that's sitting behind a patch, so you have a line of sight that goes through this halo, there's roughly an 80% chance, maybe a little bit higher, that you will see a magnesium-2 or otherwise cold or cool set of clouds. And by cool, I mean 10 to the 4 Kelvin, roughly. So about 100 times colder than the virial temperature of the halo. That is just an empirical fact from looking at pairs of galaxies and quasars. If you go out to a somewhat larger distance, about 100 kiloparsecs, then the odds that you're going to hit a cold cloud are about 50%. And then if you go out yet further to 150 kiloparsecs, then your odds in that sort of outer annulus are about 20%. And so the odds, the column densities of things that you hit is about the same at every one of these. And so it's really a binomial thing. Like, so the dice are loaded in different amounts for these different annuli. And this information has been sort of painstakingly built up over decades, starting with just surveys of absorption lines, where you compare the density of the counts of absorption lines done by Steidel and Sargent and Boxenberg and Young and folks. And you compare that to the luminosity function, and that tells you roughly what the cross-section of a halo has to be. And then people started observing galaxies near quasar sightlines, and Xiao and Chen did a lot of the early work on this, together with Ken Lanzetta and then others. It's really been revolutionized by the COS Halos team at low redshift, and then the Keck baryonic structure survey. There's an important paper by Monica Turner looking at the statistical correlations. And there's more stuff coming in all the time. So the COS spectrograph really revolutionized this at low redshift. But it all sort of comes down to this, that it's not that there's a smooth distribution of gas that looks like this. We'll show that it's clumpy. But that you see this sort of 10,000 degree gas within 100 to 150 kiloparsecs. And it's just that the odds of seeing it go down. Outside of this, we really don't know. We think that it's probably the odds continue to go down. But the problem is that observationally, the area that you have to cover goes as 2 pi RDR as you go out, and the surveys that you would do at larger distance scale unfavorably in terms of telescope time. And so it's going to be a while before we really know what happens in a complete sense out here. They're very incomplete. Yeah.
Could do it around lower mass galaxies where the virial radius is not as big.
Yes, so it has been done around lower mass galaxies, and that helps somewhat. But it means that you have to do it at lower redshifts because the galaxies are fainter, and it's harder to get a complete sample. And it's still painful. So I'll talk about ways that you might improve on that in a little bit. Yeah.
I'm aware of works done with Sloan statistically where they went out to 300 kiloparsecs from typical galaxy like this size. Mm-hmm. So this is the way probably to tackle it, is to do it statistically rather than studying individual sources, individual groups or clusters.
Yeah, there's yes and no. So if you want to study the sort of general trends in your feel like you have a really good control of systematics, then you can do that. But when you stack things, because this is again basically a Poisson thing, like the dart either hits or misses one of these things, then when you stack things, you're adding together a lot of ones and zeros, and you're not. And then if you try to measure the physical properties from that, you might mess yourself up a little bit. But you're right; it gets you the best sensitivity and the best completeness. So it's always the case with stacking that it helps you in some ways and hurts you in others. Yeah.
What does this look like for higher energy lines?
In higher energy lines. So, I forgot to say out loud, but it increases with ionization in the sense that this is magnesium-2 that's essentially neutral, so it's got an ionization potential of about a Rydberg. If you go out to higher energy, things that have an ionization potential of 2 or 3 Rydbergs, then this becomes larger. Sometimes it even goes out a little beyond the material, but it's not really clear yet. It's also the case that when you can see it, there's oxygen-6, which is even hotter, that fills a lot of this. But oxygen-6 is not. I'll get into how you can model things with ionization. Actually, I think it's my next slide, so maybe I'll get into that. Okay, so here's a fact. This is half fact and half model fact. So it's a fact that there's a rich array of lines that have varying ionization potential. So this is from Gwen Rudy's recent paper at redshift of 2. And you can see that in a single system that's near a galaxy, that you can see oxygen-6 here, carbon-4 over a velocity range of 150 kilometers per second. Silicon-4, silicon-4, there's silicon-2 here, so multiple ionization states of the same element. And the good news about this is, so this is definitely true. And if you look at the ratio of the column densities for different lines, you can actually start to untangle some of the physical conditions inside the gas there. This is a little bit of a busy plot, but basically you can untangle this if you compare ratios of silicon 2 to silicon 4 and carbon 2 to carbon 4, or other pairwise things. And because they have different ionization potentials, and if you're in photoionization equilibrium, the ionization rate goes as the 1 power of the density, and the recombination goes as 2 powers of the density, then you are sensitive. You can actually measure the density by looking at the ratio of those lines if you know what the ionizing field is. And so that's basically this axis is telling you how many ionizing photons per baryon you have. And then that's degenerate at some level with the metallicity of the gas that you're in. So you measure some combination of those two parameters by looking at line ratios. And what all these lines show is how it actually works in practice. If you look at the silicon 2 to carbon 2 ratio, what you can see is these are actually likelihood contours. So the blue comes from the silicon 2 to carbon 2 ratio, and that's one pair of ionization potentials. And you see that this area in the middle between these two contours is the favored area. And then if you look at the silicon 4 to carbon 4 ratio, then those correspond to the green. Actually, I think this is not right. This should be silicon 2 to silicon 4, carbon 2 to carbon 4. The caption's wrong. But basically that constrains your ionization in a more vertical but slanted sense. And then you combine those, and the black contours are the sort of merging of all of these different things that sort of push in from different directions. And then you lead to one solution space for the two of them. Yeah?
When you say you know what the ionization field is that coming from stars? And if so, is that spatially dependent?
So that is part of this model dependence, right? So later on, I'm going to put little warning flags near things that are model dependent. So we assume the ionizing field is coming from stars and quasars, and it's an industry to measure what that is at different redshifts. And so you're only measuring density insofar as you know what the ionizing field is. And at low redshift, it should be very uniform because the universe is optically thin. As you go to higher redshifts, that assumption starts to break down. Here's another model-dependent result, but well, it's sort of model-dependent, sort of not. So the intra-halo medium metal absorption, we think, arises in very small structures. And why do we think that? Well, some of it comes from model-independent observations of sight lines that go through gravitationally lensed objects, and then you can look as a function of separation transverse on the sky, and then look at the difference in column density between what you see in the two sight lines. And for separation smaller than about 100 parsecs here, this is a tenth of a kiloparsec, 100 parsecs, you get exactly the same column density. And then as you separate towards a kiloparsec, the separation, the difference tends to go up more and more, which tells you that this is sort of an inner scale for how small these things are. They're smaller than a kiloparsec. So this is model independent. You can do the same thing for ionization, where what you do is, if you measure a column density, which is what we do with absorption lines, and then you divide that by the three-dimensional density, that tells you how big a structure is. That's model independent. But the question is, how do you get this number here? And these are three model-dependent things in that, which I can explain later on. But the bottom line is, once you sort of crank that all the way through, you get a thickness of things going through the line of sight. And you get 100 to, sort of 100 parsecs to kiloparsecs, sometimes more, sometimes less. And the densities are sort of in between what the IGM would be and the ISM would be. We've known this for a long time, as you can tell, because this was made in PG plot and this was Super Mongo. But this is pretty robust, I think. And the first person to say it out loud was actually Jane Rigby with Charlton Churchill, where she mentioned at the end, this is in an abstract, that clouds that she measured with different species have sizes of about 10 parsecs in her case. At that size, to produce the observed redshift path density of absorption line systems, they would need to outnumber L-star galaxies by 6 orders of magnitude, right? So a way to think about that is like this. So going back to this picture, the size of these systems, as inferred by those two measurements I showed on the last slide, is given by this red dot, okay? And if you're going to have an 80% chance of hit inside there made by combining lots of those things, you have to have an awfully large number of them. And at the time that Jane had published her paper, and I actually, in the paper I wrote about this, I thought the only way you could do this is to have something that was a big sheet that would have a small line of sight thickness but a large cross section. That turned out to be wrong. But you just have to have a huge number of those. In her paper, there was a lot of discussion of what could possibly be doing this. You have little star clusters out in the IGM, and that was wrong too. And I think there's some sense of what actually might be going on now, and so we'll get to that.
But Rob, sorry,
Yeah.
10 and 100 are two pretty different numbers in the previous slide. Well,
Yep.
it looks like the top two figures are arguing for roughly 10.
Mhm.
Sorry, for 100
Yep.
more. James is saying more like 10.
Yes.
Is there?
That's because these are different combinations of ions. So the ionization lines smooth over a larger scale, and the low ionization lines are the smallest subclumps. So you can think about them as sort of clumps inside of clumps, and as you get colder, they fragment more and more. And she was measuring the coldest, smallest ones, and we're measuring somewhat hotter things. So there's basically a self-similarity or something of scales. There's some interesting papers on that. Another thing that's somewhat model dependent, but interesting, is that the mass of cold gas in the halo seems to be comparable to the stellar mass of galaxies. So there's a lot of stuff out there in the intra-halo medium. How is this model dependent? The way it's measured, this was done by Jessica Work et al. And others. She was just one who's done this, but hers was comprehensive for sure. If you take units of this, so column density in hydrogen in atoms per centimeter squared, that's a surface density. It's the same. You can convert that into solar masses per square parsec, and then you just integrate to get the mass in radial bins. But then you measure H1, not H. And so to get from H1 to H, you have to multiply by a factor of about 350. And that's your ionization correction. So if you're confident in this, then you get 10 to the 10 solar masses. And that's about the same size as the stellar mass of the disk. The star splits of gas. This is a fairly conservative number, so this is a reasonable choice. But we should just all be aware that we're seeing, we're counting a third of a percent or something of all the mass is what we see, and then we upscale it to get this really interesting result. So, and then the other thing too is that if you really have an ISM's worth of mass at 10,000 Kelvin, which is 100th of the virial temperature, the only thing it can do is go in, right? It's not in equilibrium sitting out there in the halo. And so it seems like it is subject to a cooling catastrophe that would result in stuff raining in, and then there would be a huge amount of star formation. So this is, on its face, not a stable situation. I won't go into this one too much, just because I got 5 minutes, but it is the case at redshift of 2 to 3, we're pretty sure in a model-independent way that massive galaxies drive winds into their surroundings. This is just from observations of Lyman break galaxies. I won't go into the details, other than to remind you that the distance a wind can travel is about 10 kiloparsecs per 100 megayears if it's moving at 100 kilometers per second. So we'll get back to that in a little bit. But this is a nice picture because the simulations need strong winds to come out of galaxies to reproduce the stellar mass function in the mass-metallicity relationship. Another thing that is interesting is that the intra-halo medium, these metal lines that you see, what I'm saying is it's not the case that they're demonstrably unbound. That's not the same thing as saying that they're bound. And I'll explain why. So this is the velocity shear between the redshift of a galaxy and the absorption line that's near it. This is the centroid, and then the bar shows the range of different components. And then these lines, the dotted lines here, are the escape velocity for a halo of that mass. This is for dwarfs, and this is for larger galaxies here. And because these points generally lie within the envelope here, it is claimed that this stuff is bound to the intra-halo or CGM. At higher redshift, now at redshift 2, Gwen Rudy's recent paper showed that there's some components that lie outside that range. These are not plotting the same things, but it's showing the same idea, that things that are outside of the dotted lines are unbound. And it looks like that's the case possibly at redshift of 2. Here, the thing to beware of is that when you see something that is inside, remember that if something is driving out winds looking like this, and then our sight line goes through the outer regions of it, which on a probabilistic sense, you're more likely to be at high impact parameter than low, and you're measuring a projected velocity, which is the dot product of this vector with the red one, you're more likely to be seeing things that move transverse across the line of sight. And so you're not seeing the whole velocity component. So that's something to be aware of. But it's not obvious that they're unbound. It's harder to establish for sure that they're bound. Okay. Emission line observations with IFUs. So there's a new sort of front in this. Everything I've talked about so far has been with absorption line observations in the UV, or the rest frame UV. It seems like it's not just winds that's moving stuff out. It may be the case that there's dynamical stripping. Here you can see, this is an HST image of a quasar field, and these are all galaxies. This shows the different velocities that they're moving. And with an IFU, you can actually measure the fluorescent gas that's coming out. And you see these kind of tails that come out in oxygen-3 emission. And you see that they subsume the whole area between all these galaxies here, which tells you, this doesn't look like it's only winds. There's more happening here. But I think it remains to be seen how we're going to interpret those. So I think it'll be a big area for the next decade or so. And then the last thing I want to say about this is that you can ask, how early did this intra-halo medium take its present shape? How early do we see absorption lines of this variety? So here's actually closer to stuff that I've been working on. So with fire, we look for magnesium-2. So magnesium-2 surveys in the optical go out to about a redshift of 1.8. And then we did a survey of 100 sight lines to go out to redshift 7. So the black points are with fire. And what we saw is that there's plenty of magnesium-2. And in fact, the number density of magnesium-2 that you get per unit redshift doesn't change at all over the perceptible or the observable age of the universe. And at this largest point here, the universe is only 800 million years old, right? And so there's not that much time to drive winds out and fill up a halo. It's certainly, if you want to include time to form a central object. So you can try to actually reproduce this by going to simulations and painting halos, either around objects above a certain mass cut, but that fails badly because there's not enough halos of high mass at early times. They're lower mass. If you instead paint it around things beyond a certain star formation rate, then you do somewhat better, but not perfectly, because basically things of lower mass have the same star formation at earlier times. But the idea here is that it's probably not the case that you have an L-star, 10 to the 10 solar mass central galaxy out at redshift 7. And yet you've got just as much magnesium-2 per co-moving line element as you do at redshift 0. Which implies to me that the magnesium-2 was being put there possibly as the galaxy was forming. That's sort of suggested by the fact that this is just a really small age. So this is kind of interesting. I'll skip this. This is an interesting one that we can talk about separately if people want. At very early times, there's no carbon-4 in the circumgalactic medium that we can detect, which is totally different from what you see at low redshift. But I will mention one more thing, which is that cosmological simulations, if you want to look at this using simulations and interpret it, they're generally very under-resolved for capturing the detailed physics about this. And we sort of knew that. It's not a surprise, but I just want to show how that plays out. This is the number density of magnesium-2 absorbers at high redshift as a function of their strength, their equivalent width. And then these are the data here. This shows a system of equivalent width 0.57 angstroms. This is a 3 angstrom. So this one is sort of characteristic of the strongest ones out here. This is sort of a pedestrian one down here. And the simulations get the weak ones pretty accurately, but they miss badly for the strongest ones. We didn't really understand this at first because we thought maybe the simulations weren't making enough magnesium-2. But I think that's actually not what's happening. So what's actually happening is you generate high equivalent widths by taking these lines and broadening them in velocity space. And so we think that the gas is not being stirred properly, possibly because it doesn't have enough resolution. Right? So the illustrious resolution is, in units of typical CGM parameters, is 7 kiloparsecs per sort of mass resolution element. And as I was saying, the structures in the CGM or the IHM are, they're more like parsecs or hundreds of parsecs. So we can fix that by just inflating the velocity dispersion. So how do you get a high covering fraction for small clouds? Well, this is the resolution element of illustrious. That's what we think the clouds are like. Okay, so here's the emerging picture, and then I'll get out of the way. Sorry. So I'm running a little over, but not drastically so. So the CGM or intra-halo medium has a hot but nearly invisible smooth halo gas component that has an enormous number of small embedded cool lumps that are seen in UV absorption. The cool gas has a significant but model-dependent mass that's similar to the mass in stars. And that cool gas must be far from virial equilibrium. So it must go in if it's really cold and out there. The dynamics aren't showing outflows ejecting large masses beyond the virial radius, but there's this projection effect to worry about. I think the pollution must have begun very early as things that would eventually become L-star galaxies were forming, but they hadn't yet relaxed into disks. And that the current simulations fail badly to produce some of these features because of their dynamic range, at which point maybe the thing to do is pass this over to Cameron. I can talk about some of the other things, but I'll stop here and let you get through your stuff.
And then we'll check.
Yeah.
Or battle.
Yeah, we'll do that.
Okay, let's thank Rob first.
Okay. Do you want to do clarification? Do you want to do clarification questions? No. Okay. You were going to get clarification questions, but you're not actually going to get them. You'll just have to remember them for the end. Yeah. And prepare yourselves to vote on whether from here going forward it's going to be the CGM or the IHM.
Oh,
We're
right.
going to get a vote on this at the end. It will be part of the battle. So I want to introduce Cameron for the theoretical portion of this talk, although he does do some observations also. Novaces?
Oh, there we go. Okay. I was going to fail the theoretical person here if I couldn't actually get my slides.
Yeah, you're going to have to just talk. So Cameron is a NSF postdoctoral fellow at Caltech. He's an expert in using simulations to understand the CGM, as Rob mentioned, how gas gets in and goes out. He's also an expert code developer. He's worked extensively on the YT analysis suite, which for anyone who went to the event on Monday, the Seamless Astronomy on Monday, you will know it's pretty cool. I saw a demonstration by Anna. It was neat. Yeah, it was great. He also works on ENSO, and he works on a set of tools to make synthetic observations of the CGM. For those who don't know Cameron, he's also a crazy
person.
Crazy bad. I was going to say a word that I shouldn't say. He's a very good triathlete, which is cool. And he's also really, he's a leader in education and public outreach. He's the director for education and public outreach at Caltech. Take it away, Cameron.
Thanks, there. Hi, everybody. So it's a hard act to follow, Rob started out, but I'll try. Okay, so the movie you're looking at here it's a movie showing the circumgalactic medium of a central L-star halo. So this is like a Milky Way mass halo. The white circle represents the virial radius of that galaxy as it grows with time. We're looking at projected gas column density, the temperature of that gas, and then just the absolute value of the metallicity. Oh, and these are from the fire simulations, not to be confused with the fire instrument. I had to fight fire with fire in battle. So, anyway, okay, so like what Rob pointed out, the volume over which the gas in the halo exists is substantial. So even though the column densities of the gas that are out here are very, very small relative to the ISM in the galaxy, you're dealing with a volume that's like 50,000 times larger. So you can actually contain potentially more baryons in the halo than you actually have in the disk of the galaxy. So it plays a really substantial role. Lots of different temperature regimes. We're not pretending that this resolves all the structure. As Rob pointed out, a lot of the structures are too small for the resolution elements that we have in the simulation. And as you can see, there's a lot of stuff going on. We're blowing stuff out potentially beyond the virial radius of the system and blowing metals out beyond the virial radius of the system. So this can pollute the region around the galaxy as well. But the question that I like to pose initially is, this is really important for a variety of reasons. First of all, understanding galaxy evolution, but second of all, trying to understand how galaxies quench themselves. This is still a huge, huge issue. One way in which we potentially could quench the galaxy is cutting off the gas supply that gets into the ISM of star-forming fuel from the CGM. Or just quenching the amount of gas that gets into the CGM as a whole. So what I'm going to ask you guys to do, an interactive discussion here, initially is identifying
effectively 5 different ways that we can get cool gas into the halo, either from external means or internal means. And you can get some insight just by looking at this repeating film. So do people have ideas, general global mechanisms that you can get gas into the halo, either through external or internal means? You can shout if you want.
Outflows.
Outflows, right. So outflows, you can see all these popcorn bursts of gas that are flowing out from star-forming regions. Also AGN outflows, so winds will pollute this halo with metal-enriched processed gas that's coming from star-forming regions and AGN. And even AGB winds as well. So, good. Very good. I didn't prompt her to do that. So, other ways that you get gas in the halo.
Substructures?
Substructures, yes. So like you can see satellites coming in as they fall in, and when they fall in, they bring in their own gas. Sometimes it's polluted and processed, and sometimes it's more primordial, depending on the star formation rate. Good. Okay, so satellites are coming in. Other methods.
And fall from cosmic filaments.
Cosmic filaments, yes. You can see that there's kind of a global filament going across this, so you should have some, depending on the halo mass of the primary galaxy, you'll have some smooth filamentary accretion that occurs, or at least is predicted to occur, but we don't have a lot of observational evidence for it so far. So 3 things.
Condensation.
Condensation, yes. So condensation from kind of the hot IgM is coming in, or potentially when one of those filaments comes in and it runs into the virial shock of the galaxy, it heats up and then it kind of slowly percolates down and cools and condenses. So 4th. And I have one, it's kind of a meta thing, so I'll just spit it out there. Precipitation. So precipitation is the idea that you have gas that's out here in kind of a hot state, and eventually it gets cool enough to just kind of precipitate out, condense out of that hot medium and turn into a cooler form and potentially fall onto the galaxy. So those are my... Oh, I was supposed to ask that question. So those are my 5 things, so very good. Give yourselves a pat on the back. But you can see 3 of these things are nominally external means, and then 2 are kind of internal means. But it's being fed by a lot of different sources, which is why the CGM is kind of a pain in the butt, because it's touching on a lot of different physical mechanisms, and you have to get them all right to get it right. And we don't get it right. So, oh yeah, and I have a really cool demonstration. There's a graduate student working with Claude-André Fauché-Giguère at Northwestern who put out, his name's Zach Hafen, he put out a paper 6 months ago, and part of it has this visualization called, using this code called Firefly. I'm going to see, live demos never go well, so we'll see if this actually works. This may not work. They spin. You're supposed to spin, you know.
No, it spins. It does.
Oh, it is spinning. Okay, there we go. So it's, well, we'll just see how this works. So the cool thing about this is we can show that that disk represents the disk of the galaxy. We can show where the various particles are from. This is again from the fire simulations. So the green particles here represent wind. So these are, like Erica pointed out, winds, outflows generated from within the galaxy. This is just there at redshift 0.25 for this particular system. Again, it's an L-star system, where the distribution of where those gas elements exist.
How the wind brings gas into the galaxy? It brings
it brings it from the galaxy into the halo. Right now we're talking about getting gas into the halo. So that's from an internal means. If we look at satellites, there's our satellites. Those have been absorbed, and they're on their way potentially in. If we look at the satellite wind, so that's the stuff that's being kicked out from those satellites into the halo. And then finally, let's look at the just general IgM accretion. So that's just all over the place. You see some kind of clumped structure potentially. I don't know. I don't really understand why there are clumps there. Maybe there's condensation that's going on, or precipitation from the IgM at that location. But for the most part, this is kind of a spherically symmetric business.
What happens if you plot the satellites on top of that? Maybe it was also associated.
Oh yeah, I think it is. I think you're right.
Mystery solved.
Mystery solved. The other thing that's nice about this is you can look at, this is the same volume. I'm getting it spinning again. We can look at these are the trajectories of those particles for the last gigayear. So these are the wind particles that originated here and are just like spraying out everywhere. And this looks like a party favor. But if you look at, for instance, the satellites, obviously it's much more correlated, and you can see the structure as it travels through the halo, along with their winds that are coming off of them. And similarly, if you look at the IgM accretion, it's kind of coming from everywhere. You don't see a lot of filamentary in this particular case.
So do you guys also look at the mixing between the accretion going in, because you would expect that to be the primordial, right? Compared to the winds, which would be metal enriched?
Oh yeah, absolutely, absolutely. Because depending on the observational technique that you use, if you're looking at metal lines, there's not a lot of metals in the IgM accretion. You have to wait until it mixes with the...
But the observations are pretty flat, right?
The observations...
For the metallicity? The observations for the CGM.
The
costs? Isn't the cost stuff pretty...
It depends on what. For 06, yes, it's relatively flat. But 06 is kind of the anomaly in terms of all the observational species. But you're right. As you go out an impact parameter or projected distance away from the galaxy, the oxygen 6 values are relatively flat, around 10 to the 13.5%. Okay, I just wanted to show that because...
For Cosmological, they selected things based on galaxies. So if you go and select absorption systems, you find much lower metallicities out there sometimes.
Okay.
Because they look for things where they move there to galaxies.
Yeah.
Okay, so I just want to step briefly through all of these things that we've just discussed, citing some relevant work that brings up some caveats to these. So this is our global picture of cool filamentary accretion. Again, you probably learned in your cosmology or galaxy evolution class, these are predicted to occur where you have gas falling along cosmic web filaments into the galaxy. If the galaxy is low enough mass, and it seems to be somewhere around a halo mass of like 10 to the 11th or so, then these filaments can just sneak right into the galaxy and deliver cool gas directly to the galaxy. And this was done by work, Duchan was a postdoc here, worked with Lars and did a lot of this stuff, which is great. It hasn't really been observed, so there have been some cases where people think, oh, maybe this is a filament that's like Chris Martin's emission stuff kind of invoked that there were these filaments associated with a high redshift galaxy. It's not really clear that these have actually been observed. So, I don't know, maybe theory's wrong. And this is from Zach's paper showing the relative contribution for a 10 to the 12th solar mass halo, a 10 to the 11th, and a 10 to the 10th, with the radius from the galaxy and then the various different components for IgM, satellite, and internal winds. So you can see that the bulk of the material that makes up the halo, at least in the fire models, for an L-star system is IgM accretion, as opposed to the internal or the satellites. The satellites are definitely subdominant. Okay, but in terms of, as I said, if you've got a hotter halo, a more massive halo, you have a virial shock. And that gas, when it comes into the filament, it shock heats. And it heats up to 10 to the 6, something on the order of the virial temperature of the halo. And 10 to the 6, this is a cooling curve for primordial metallicity and for solar metallicity. And you can see the difference between like gas that's coming in at a few times 10 to the 4th has a very high cooling rate, so it can remain cool very effectively. But when you jump up to 10 to the 6th, your cooling rate drops by an order of magnitude, and then it's not so effective at cooling. So it hits this virial shock, and it's heated up, and it can't easily fall onto the galaxy in such a hot state. So it kind of slowly percolates in, and that's how you get the thing, the condensation like John Force was talking about. So that ends up being kind of a hot spherical accretion. You'll note that Zach Haven didn't include that in his IgM analysis. He didn't differentiate between cold and hot, but it tends to be less filament structured and less kind of direct. Dylan Nelson, when he was a graduate student here, did some work in this, indicating that with better models like using a repo instead of gadget, you can potentially make these filaments less effective at delivering their gas, and it's more like the global condensation model. And part of the connection that I find, there's a paper that came out this year by Nir Mandelker, looking at, in very, very high resolution cases where you're able to resolve the filament very, very well, you'll start to get Kelvin-Helmholtz instabilities along the interface of that filament, and it effectively can disperse. That gas isn't effective at getting to the galaxy itself. It disperses on the way in, and it can lose like 10 to 50% of its overall material before it actually can deliver it to the center of the galaxy. This is a time series of the filament with time, and eventually it just kind of disperses. So this may tie into the results that Dylan and Lars and the Illustris crew were seeing. Rather than increasing resolution, they were increasing to a higher order method using moving mesh, and potentially that's the reason that they saw what they saw. Yeah?
So in your simulations over here,
yes.
are you done in 2 or 3D? Because in some of Mike McCord's work showed that your results actually depend on the image.
They did it in 2 and 3D.
Okay.
They've done a series of papers. The third paper, which is this one, which is published this year, has 3-dimensional, and they do cite that you get different modes of the Kelvin-Helmholtz instability that occur in both 2D as well as 3D. So, yes, that's a very good point, though.
The previous plot you showed about the cooling curve. So, what's the cooling time, and shouldn't it very strongly depend on the assumed volume density of the gas? So what do we know? It
depends on the volume density, and it depends a lot on the metallicity of that gas as well. I'm just using kind of global arguments at this point because I'm trying to review. But
because the difference is not that big. I mean, it's a factor of 10. But if you assume if there's some clumping, you can maybe potentially get this factor of 10 increase in density, and then get enough cooling.
Well, it definitely plays a role in whether or not we see the filaments. We don't see a lot of evidence for the filaments, but we also didn't see a lot of evidence for the precipitation that would occur if you had more effective cooling as well. But I'll get into that in a second.
So then, since you expect the winds to get put in higher metallicity material, then would you expect that the condensations would just be due to the winds mostly, if you don't have a lot of efficient mixing between
You might, and that's what people are looking for in the models. In my models, though, I don't see it in the metal-rich stuff, I see it in the dense stuff.
Well, yeah, but you don't see a metallicity dependence on it, because you increase cooling by metallicity.
It depends on how structured your winds are. If they're channeled out, and you get a high metallicity in this region instead of a global metallicity, then you'll definitely see the precipitation occurring in that region. The Punky satellite accretion that we talked about, this is kind of a subdominant effect, so I'm not going to talk too much about it, but, whoa, that wasn't supposed to blow up. Okay. For the winds, again, the winds are kind of a subdominant component, but they can contribute to, I don't know why that's doing that. Okay, I messed up my slides. But, so there's, pretend that, okay, I got it to work. So when these winds occur, let's say they have jet material. There was a bunch of work done by led mostly by Todd Thompson, but other authors as well, indicating that when you generate supernovae outflows, they're nominally very hot, 10 to the 6, 10 to the 7, and they're flying out there, and let's say they entrain some cold gas with them and take them into the outer halo. They'll probably get ripped up by Rayleigh-Taylor and Kelvin-Helmholtz instabilities on the way out because they're flying at such high velocities. So you can't directly deliver the cold gas from within the galaxy out to the halo because they shred. But what you can do is as they travel into the outskirts of the halo, there's a lot more volume there, so they adiabatically expand. And when they're expanding, they cool substantially, and then radiative cooling takes over as well. So it's like planting, when you initiate a jet of supernovae-enriched material from the interior of a galaxy into the halo, you're not necessarily taking this cold gas and throwing it out there. You're planting the seed of what will eventually turn into cold gas in the halo through mixing of the metals with that ambient material and then allowing cooling once it gets out there. And it cools because it's adiabatically expanding. This was looked at by Evan Schneider and Brent Robertson and collaborators, and Todd. So this is a movie that they did with Evan's code called Choya, which is an extremely high-performance GPU code for doing this. This is a small region. You can see 1 kpc for scale, so I think it's like 20 kpc above the disk and maybe 10 kpc surrounding the disk. And this is the temperature. She didn't include a color bar, unfortunately, but basically The dark purple represents cool gas, and then the lighter stuff is, so this is like 10 to the 4, and this is like 10 to the 6. And over time, you start to see a buildup of multi-phase structure where it's a mix between the cold gas and the hot gas as it travels out into the halo. And the key behind that was having a high mass loading factor and having your star formation going off distributed, like clustered, but not just in a central location that's blowing stuff out.
The ripple that you see there, is it a numerical artifact or the real?
The ripple, when it was like,
Yeah,
it was
like
pulsing
you
kind of
just see
outward,
it.
yeah. I think that was some weird resonance in that particular simulation. That's
like,
not
like
a generic.
Right now. See,
Here, so,
Oh, was it?
can we let him finish?
Oh, sorry.
Oh, no, not you.
I think it was an artificial thing, but the filamentary structure looks consistent with what the predictions were from analytic stuff with like Todd Thompson's before. How am I doing on time? I should finish. 2 minutes. Okay, sure. All right. So
2 minutes.
1 to 2 minutes. Consistent with that, there have been a number of isolated, they're called cloud crushing simulations, where you have a clump of gas. This is meant to be GMC or something on that scale, and you're hitting it with a hot wind, and over time you erode that structure because you're slamming it with a hot wind. So Max Gronke had work on this in the last year, and this is related to work done by your own John Forbes, where over time, as I said, the metal-enriched material in that GMC starts to mix with the ambient medium, and it effectively cools. So even though you're eroding that structure, you're providing the seeds that you can actually build up more cool gas in its tail than you had in the initial structure. And what's more, that's traveling, co-moving with the hot gas now, so you're moving it with the velocity of the winds that are taking it into the outer halo. And I'll talk about precipitation because precipitation rules. Let's see, where's my cursor? There it is. I have to zoom forward in this movie because it's really, really long. The idea is this is an isolated galaxy simulation done by a colleague of mine, Devin Sylvia at Michigan State. This again is density, that's temperature, and that's metallicity. So in this state, you're slowly having a star formation rate of like 1 solar mass per year, so Milky Way-ish. And you're slowly percolating metals out here. Eventually, the metals, as you distribute them into the halo, they're decreasing the cooling time. You're getting more effective cooling until at some point you just have a precipitation event, which should happen in like 10 seconds, where all of a sudden the gas is really, really effective at cooling, and it can start precipitating into cold structures and raining back down onto the disk, spurring on the star formation. Here, see? Get this, it just all of a sudden happens. It rains down on the galaxy. It's supposed to be cyclical, where you turn on star formation. Of course, the star formation will then heat up the surrounding medium and turn off the precipitation, turn off the cycle of star formation. That doesn't happen here. It goes up to like 100 solar masses per year of star formation, and it's going like gangbusters. So we haven't worked this all the way out, but what's key about this is it appears to occur, this is an analytic prediction. When we apply it in simulations, it only seems to occur in idealized isolated galaxy simulations like this. When we do them in cosmological simulations, we can't reproduce this. We can't reproduce just this spontaneous manifestation of cool gas precipitating out of the halo. This is as best as we can do, and this is I'll make this my final slide. These are from my Tempest simulations. I put out a paper 6 months ago. Cosmological simulations at very, very high resolution throughout the box, so you can resolve the individual structures, resolve the individual things. In this case, these are two identical simulations. The one on the right is at higher resolution. The one at the left is lower resolution, and you can start to see a filament that's showing, and it slows down. This is a phase diagram showing the density and temperature. Sorry, I'm saying a lot of things. I'll pause this. Oh, I didn't pause it. Okay, I'll get to here. And what you can see, so there's a filament here when you have resolution that does not show up when you don't have resolution. And the circle represents the region that we're taking and we're putting into this phase diagram to look at its density and to its temperature. And what you can see is that you see those little stuff that's just forming, it's just condensing out of that. And if you look at the phase diagram, it has like an order of magnitude higher density and cooler temperature So the point is, when you have the resolution to actually allow you to seed the precipitation, either through density or through metallicity of the gas, you get precipitation. But we're seeing it preferentially in a filament as opposed to some sort of ambient metal-rich gas. This is not metal-rich. This is a filamentary structure coming into the galaxy. But we're seeing like thermal instability going off and precipitating into these cold structures. Anyway, there was lots more I wanted to say, but 20 minutes isn't a lot of time, so we can chat about stuff.
Great.
And we can battle.
Many.
Oh yeah, I know.
Slides. Okay. Do you wanna get up here? We can do some battle.
Yeah. Can I show something? Just
Yeah, sure.
It's just the slide that I missed, but I just want to. It really just emphasizes the importance of what you were saying. So that's a bad way to start battle. So this is, I've worried for a while, and Jane did before I and others. Why my thing is not showing?
No, I did the same problem.
That you have all these cold things that have an aggregate large mass that are sitting out there in the halo, and they shouldn't stay. And so I think that what you were talking about with precipitation and other things is really getting onto it. So like, what if you have all these little tiny cool clumps, but they're very short-lived? And so the idea, instead of a ballistic model where you're shooting rocks from a galaxy out into the surrounding area, that, like you say, it's filling that area with metals, but once you do that, you can cool. And so since you have stuff that's 1,000,000 degrees and stuff that's 10,000, it's different by a factor of 100 in temperature, which means it's different by 100 in volume or size. So basically, it just shrinks like that and falls in. But the idea is that maybe the only way you can avoid an overcooling, and what happened in your simulation, is if it doesn't ever reach the disk. Either it lofts it back up or it shreds from an instability. Mm-hmm. So if the Kelvin-Helmholtz or another instability shreds before it reaches the disk, you avert the overcooling. This looks a little bit like a weird version of convection, right? So that you have cooling somewhere outside, but instead of by radiative, like black body, it's through atomic line emission, and then it does that, and then it sinks, and then something happens as it approaches the disk to heat it up, to keep it from going all the way in. And what I don't really understand is what exactly is providing the heating power. Is it thermalization of galactic winds? But this avoids needing to transport the wind material out, hundreds of kiloparsecs, which it violates the early appearance of magnesium-2. And also, I don't think anybody knows what sets the inner scale of this turbulence, or like when it shreds. And so that seems like an outstanding question. Otherwise, you need infinite resolution in your simulations. Right. So it's nice to know when you're done. So
yeah. So something that's relevant to that is no, that was great. Something that's relevant to that is many of you may be familiar with a paper that came out by Mike McCourt in the last year or two. It's called "On the Scale of." I can still talk, right?
Yeah,
I shouldn't talk. I should let people go.
We could have someone ask a question.
We have 4 or 5
Oh,
minutes
yeah.
more because we started with 4 times.
Sorry, God.
Finish your sentence.
What? Huh?
Finish your sentence.
Oh. Yeah. On the scale of cool gas, essentially he did these very, very large, and this was referenced in the back, very, very large, high resolution, well, not large, not spatially large, very high resolution, expensive computational models to look at thermal instability and the fragmentation of gas into a multi-phase medium between cool clumps at 10 to the 4 Kelvin and hot kind of medium separating them at 10 to the 6 Kelvin. And he only found convergence at sub-parsec scales, which is something that we're not going to be able to do in idealized galaxy simulations or cosmological simulations or anything like that. But the point is that a direction that the field, both from the observational side as well as the theoretical side, is kind of moving is that if you have cold clumps that are in these very small, up till now unresolved structures, you end up with kind of an atmospheric cloud-like structure where when you look up in the sky, we see clouds in our sky, and those clouds don't consist of an enormous water droplet that's the size of an airplane. They're distributed and consist of small, microscopic scale water droplets, and that provides you with the covering fraction of that's observed, but it also provides, because there's a lot of surface area, a means of keeping it aloft instead of just collapsing down. So it resolves a lot of these things. Unfortunately, it makes it really hard to computationally model because you can't have a box size that's 100 megaparsecs and then be resolving something that's sub-parsecs at the same time. So maybe the method forward is subgrid models or something like that. But this is definitely 4 different researchers, one of which was Josh Suresh, who was a graduate student here, myself, and then Freekje van der Voort and Molly Peebles all put out papers within like 2 months of each other, basically coming to this community. So it's pretty exciting. I'll stop you after.
Well, following up on this issue, so what you essentially then get in your unresolved simulations would be wrong cooling times in there. Is there an observational way of
testing
grading
that?
this?
The main thing is to look at the observations, make synthetic observations of the simulations and compare them against the actual observations that are being taken, because different cooling times will result in different ions being abundant or absent. And in general, almost all the simulations, no simulation can self-consistently reproduce the observations of like, there's this much O6 here, and there's this much carbon-4 here, and there's this much magnesium-2 there. But as you increase the resolution, the trend is that you get more of those ions present because you're better resolving. They're still unresolved, but you're better resolving those individual unresolved components.
All right, sure. Last question.
Sorry, guys.
So it's interesting. I was very interested to hear all these things. I studied multi-phase ISM, and we have the hot gas is 10^4 and the cold gas is 100.
So yeah.
But I will just forward the question that I was asked when I had my talk. And this is about the scale again. So what sets the scale of these droplets? There should be some physical mechanism that, for example, in clouds, this would be the surface tension of water against the pressure of the air and things like this.
That's right.
For us, what?
So we aren't perfectly sure that it's subparsec. The models that Mike didn't have additional plasma physics effects. He didn't include thermal conduction. He didn't include cosmic rays or magnetic fields, anything like that. So there are additional models being done by a number of groups to include these effects, which could potentially increase that scale. It's not going to bring it up to 10 kiloparsec scale, but it could potentially increase it to greater than a parsec, maybe 5 parsecs or 10 parsecs in scale. Because you imagine if you have thermal conduction effects, the distance which a hot, high energy ion can travel into a cloud, if it goes all the way through it, well, then you aren't going to find objects on the scale that's smaller than that.
So you say it's generally conduction.
Conduction will be one of the major components.
Yeah, because for the colder ISM, conduction gives you a very small scale. So
I see.
No, I mean it's
right, but
it's
for this we've got like 10
something
to the 6
wrong,
Kelvin gas that will be able to travel through and will wipe out anything smaller than a parsec or something. Or it should. It should. But this is definitely an ongoing thing that I'm sure you'll see papers about this in the next year.
People are trying to figure out what the inner scale is. Conduction is one. I'm not an expert on it, but I think there's other mechanisms. We can introduce pressure into these systems and prevent them from collapsing to arbitrarily small.
Turbulent pressure,
cosmic rays.
Yeah. The other problem is that the densities that we're dealing with are very, very low, and so almost the fluid equations break down because the mean path length for individual particle interactions is on the order or sometimes a little bit larger than the structures we're trying to measure. So it may not be appropriate to deal with in a totally hydrodynamic fashion, which is what we've been trying to do because that's what we have, but it may need more sophisticated plasma physics techniques.
All right, let's thank these guys. We can discuss it.